So in 2.8, we're going to go through function operations and then composition of functions. So first thing we're going to talk about is how do we perform our normal addition, subtraction, multiplication, division in terms of functions. So notationally, all you're going to see is we're going to have two functions f and g. For this first one, if you have f plus g of x, that just means you're going to add these two functions together. F minus g of x means subtract those two. Fg of x means multiply, and then f over g tells us to divide. Because we're combining these two different functions and each of them has their own respective domain, we've got to be careful with what the domain of this new function is going to be. So in these first three cases, when you're adding, subtracting, or multiplying, you just want to make sure that the values you pick work for both of the functions. So I'm going to look at the intersection of f and the intersection of g. Whatever values work for both functions will be the domain of this new function we get after the operation. In the case we have division, we have a bit of a problem because we don't want to divide by 0. So for here, we have something a little extra we have to consider. You want to figure out the domain of the original function, f, domain of g. You also want to make sure you pick values that don't cause that denominator to be 0. So basically, the same domain as the top three, but now you're also going to exclude values that cause the denominator to be 0. So let's go through some examples. We've got two functions. F of x is x squared plus 3. G of x is going to be the line, negative 2x plus 6. And we're just going to evaluate a bunch of these. So you absolutely could go through and you could find the function f plus g first. But really, all this means is we're going to take f of 3, add to it g of 3. So when we find f of 3, replace x by 3, so you get 3 squared plus 3. G of 3 is negative 2 times 3 plus 6. Once you find these two values, then you just add them together. So that's going to be 9 plus 3. This one will be negative 6 plus 6, which is nice. This just becomes 0. So this becomes 12 plus 0. So this particular function evaluated at 3 would be 12. If we want to take f minus g evaluated at negative 1, that's going to mean we just take f evaluated at negative 1, subtract g evaluated at negative 1. So for f of 1, you get negative 1 squared plus 3. G of 1 is negative 2 times negative 1 plus 6. So we just need to simplify. You get 1 plus 3 minus 2 plus 6. So we get 4 minus 8. So this function evaluated at negative 1 would be negative 4. If you want to take f times g evaluated at negative 3, you're going to take f evaluated at negative 3, multiply it by g evaluated at negative 3. So that gives us, again, negative 3 squared plus 3. G of negative 3 is negative 2 times negative 3 plus 6. So that's 9 plus 3 times 6 plus 6, really 12 times 12. So this would equal 144. So for f over g evaluated at negative 1, we're going to take f evaluated at negative 1 divided by g evaluated at that. So f evaluated at negative 1 squared plus 3. G of negative 1 is negative 2 times negative 1 plus 6. So cleaning this up, it's 1 plus 3 over 2 plus 6, or 4 over 8, which you can simplify. It is just 1/2. Okay, but if you left it as 4 over 8, that's okay too. Let's try another example where we actually find the domains. So we'll find these particular functions and then go through and find the domains of these new things. So we've got f of x is a square root function. G of x is our identity function. So first and foremost, we're going to have to find domains. So I might as well start with finding the domain of the two functions that are given. So we've got a square root. We need what's underneath the radical to be greater than 0. So x has to really be greater than or equal to negative 3. So the domain of f would be from negative 3 to infinity. When we look at g, there's no problematic numbers. So really the domain of g is negative infinity to infinity. So let's go ahead and start with f plus g. All we're going to do is add these two functions together. So f of x is the square root of x plus 3. G of x is x. So you can't simplify them, you can't add them, they're two different things. This is as far as you can possibly go for the addition of these two functions. But now, when we go and talk about the domain of this, I've got to consider a couple different things. I've got to look at what is the domain of f, I've got to look at what is the domain of g, and then I can go through and figure out what the domain of f plus g is. So first, for f, that's our root function. I can equal -3, and I can take anything bigger than it. For g, I have no restrictions. I could really take anything. So for this new function f plus g, I have to take what's in common to the two. So they both can equal -3. That's going to be in their intersection. The left half for -4, -5, any value below -3, that causes problems for f, so it's not going to be in this intersection. But I can pick any value over here because that's in common to both of them. So the domain for this new function f plus g happens to be exactly the same as f. It's from -3 to infinity. So now let's go through and let's do a division one. So this is one that's a little bit harder. If you did f minus g, if you did f times g, it would end up with exactly this same domain. But f over g has a bit of a problem. So we're going to take f of x divided by g of x. So you get the square root x plus 3 over x. And again, can't simplify this. I can't bring that x under the radical without doing a bunch of stuff first. So it's got to stay like this. So now I've got a couple things to consider when I find the domain of the division of these two functions. I'm still concerned with my function f. I'm still concerned with g. But now I also have this problem because g is in the denominator. So we have some issues when x is equal to 0. It originally worked fine, but if I try to plug it in now, I'm going to divide by 0. So I also have to take into consideration, where does g not equal 0? So for f, again, I could equal -3 and anything bigger than it. G really doesn't give us any problems itself. It's just x, so you can plug anything you want. But then we have this issue at 0. That causes g of x to actually equal 0. So I need to exclude that from our domain. So when I go to find the domain of f divided by g, I need what's in common to these three pieces. So all of them can equal 3, -3. So I can equal that. We have this problem right here at 0. I can't equal 0. Anything in between is good. That's on all three number lines. And anything to the right is also good. It's on all three. So our domain is from -3 to 0, and then from 0 to infinity. So pretty much when you go through for the division one, just take a look at that resulting function. What are some problematic values in your denominator now? So the next thing we're going to go through is our second type of kind of unique operation we have. So we've got our standard operations. Now we have something that's called composite. So you might hear it as fog or goff. So really what you're going to see is this open circle. So be a little cautious when you write it. You don't want to confuse it with the multiplication dot. It is a unique thing. So f of g of x means you're going to take the function f, which is the outside function, and you're going to evaluate it the inside function. So it gets evaluated at g of x. So really when you see this notation, it's the same thing as saying f evaluated at g of x. Okay. So the way this kind of works is you first evaluate g at whatever x you input, then the output of g becomes the input for f. So pretty much you're going to input an x value into g, you'll get some y value. That value gets input then into f, and you get your output of your actual function. So the domain for these can be a little bit tricky because you might get a resulting function that looks really nice and has no issues. But because of the way this is defined and you start by evaluating at g of x, the domain of g is going to be important. So the inside function matters. you need to make sure you can pick values of x that work for the inside function first. So the way this is going to be calculated is you look at the domain of g, or whatever your inside function is. Then you're going to get this nice function at the end, which you're going to call the domain rule for this composite function. So pretty much look at the domain of the inside, then see, once I go through and simplify this composite function, what does that look like and what's its domain? The intersection of those two will be the domain for the composite function. So the best way we can kind of see what this fully means is, let's do an example. We're going to be given the function f of x equals 2 root x, and then the function g of x, which is 4 minus x squared. We want to find both composite functions, f of g and g of f, and then find their respective domains. So first, we need to find the domains of both of these anyway. So if we look at f, it's a square root function. You need the inside to be greater than or equal to 0. G, not a problem. You can take anything, square it. You're good. It's just a polynomial. So now we can go through and actually find these composite functions and use these two domains to help us out. So first, f of g of x means we're going to take f, evaluate it at g of x. So what we're going to have is g of x is 4 minus x squared. So anywhere I see an x in my function f, it's going to get replaced by 4 minus x squared. So what's underneath the radical gets replaced by 4 minus x squared. So this is our resulting composite function. Now we want to figure out the domain. So I'm concerned with this inside function because pretty much I need the values of x that I pick to work at any point along these lines. I have to make sure I'm writing a valid expression every single step along the way. So because g is on the inside, that's important. But g itself has no issues. You can pick whatever you want. So now we want to go through and we want to look at the expression we ended up with. We want to see what is the domain of this piece, compare it with the domain of g, pick the values that are in common. So now we want to find the domain of 2 square root of 4 minus x squared. So since it is an even root, we need what's underneath that radical to be greater than or equal to 0. And this is where our interval testing comes back into play. So you really have to factor this out. 4 minus x squared, difference of perfect squared. It's 2 minus x, 2 plus x. I need that to be greater than or equal to 0. So really, I've got to pull back that interval testing again. So I've got two important numbers, 2 and negative 2. So we split our number line based on that, and then we do testing in each to see if the interval works. So if we start with something in interval 1, negative 3 falls in there. So if we plug that into the expression, you get 4 minus negative 3 squared. We want that to be greater than or equal to 0. That's 4 minus 9 is greater than or equal to 0, and that's a bit of a problem. So this interval doesn't actually work. If we go to interval 2, 0 falls in there. If you pick 0, that's 4 minus 0 squared. That's definitely good. So everything inside interval 2 is going to be good. And then interval 3, x equals 3 falls in there. So you get 4 minus 3 squared again, which is 9. Doesn't work. So interval 3 is problematic. And our endpoints will cause us to exactly equal 0. So we'll get the square root of 0. And that's perfectly fine. So we can equal those endpoints. So the domain of this ending function is from negative 2 to 2. So now when I want the composite function, I need to go through a few things. I need to see the domain of the inside function, the domain of the end result expression I got, and that will tell me the domain of the composite. So for g, we could be whatever we wanted. For the ending function, 2 root 4 minus x squared, you can only equal negative 2 to 2. So for the composite function, I want the overlap between these two, which is going to be exactly from negative 2 to 2. So the domain of the composite function is -2 to 2. Okay. So now let's go through and find the second composite function, g evaluated at f of x, or GOF in this case. So you want to be careful. It's not necessarily going to be the same function as the other. They can't reverse the two. G of f is not the same thing as f of g. Sometimes it could happen, but those will be very special functions that it happens for. So what we want to do is we want to take g and evaluate it at f of x. So f of x is 2 root x. So anywhere we had an x in our original expression, it's going to get replaced by 2 root x. So remember the function g was 4 minus x squared. So I'm going to get 4 minus 2 root x squared. So be careful when you distribute that square. It distributes to both. So the 2 gets squared, the root x gets squared. And now you get 4 minus 4x. So this is where it gets important to kind of care about that inside function. You need to make sure at every step along the way you're picking values of x that work for every single one of these equal signs. So although this end expression, it looks like I can plug whatever I want into it, I can't here and I can't here. So I still have problems when x is a negative number. So I need to make sure I'm excluding those values. So we start with the domain of that inside function. So if we look at the domain of x, of f, we need x to be greater than or equal to 0. Now we look at the domain of the end function or expression we got, which was 4 minus 4x. There you have absolutely no problems. So when I go for the domain of the composite function, I care about the function f, I care about this end expression, and then that'll tell me how to go through and find the domain of g of f. So for f, you can pick 0 and anything bigger than it. For 4 minus 4x, you have no issues whatsoever. But that means for our composite function, I really have to start at 0 and go to infinity. So although it looks like I can do 4 minus 4x, I can plug in whatever I want, I can't because of how this composite function was found. So the domain of the composite function is from 0 to infinity. So the last thing we're going to kind of go through with these operations with functions is dealing with that average rate of change. We've seen how the average rate of change measures how much a function increases or decreases over a given interval. We found it by finding the slope of the line that connect those 2 points. So pretty much if you have this function f of x and you're looking for the average rate of change over this interval, you can look at the line that connects these 2 points. And you might hear this called a secant line. So the average rate of change is going to be the difference in y values over the difference in x values. So this first point here would be x1, the function evaluated at x1, and this is x2, the function evaluated at x2. So the slope of the line connecting them is your average rate of change, f of x2 minus f of x1 over x2 minus x1. Another form we can actually do to find this average rate of change comes from making a change of variables. So really if we look at the two x values, there's some distance between them. I'm going to call it h. So we're going to let h be the difference between these x values. So really what you've done is you've started at x1 and you've added h to it. So you can rearrange this substitution to get x2 is x1 minus h. So our average rate of change, we can just rearrange a little bit. So x2 is x1 minus h. And then x2 minus x1 is exactly h. So this becomes the function evaluated x1 plus h minus f of x1 divided by h. So this is actually what we call a difference quotient. So you can do this for any x value. You don't need to be putting that x sub 1. Just call it x. So the difference quotient is the function evaluated x plus h minus f of x divided by h. The only stipulation is h can't be 0 because you can't divide by 0. So let's get some practice. Let's find and simplify an expression for the difference quotient for the function that's given, which is 3x minus 2x squared. So you absolutely could just jump into plugging everything in here, but I tend to like to take it step by step instead. So I'm going to find f of x plus h, and then I'll find their difference, and then I'll divide by h. So I don't have to go through and write this like gigantic expression every single time. So let's start by finding f of x plus h. Anywhere you see an x, it gets replaced by x plus h. So we get 3 times x plus h minus 2 times x plus h squared. So before we can distribute that -2, we've got to go ahead and actually FOIL this expression out. You can distribute the 3 first, but x plus h squared is x squared plus 2xh plus h squared. Now you can go ahead and distribute that 2, -2 even. So you get -2x squared minus 4xh minus 2h squared. Now there's nothing I can do to condense this. I don't have any like pieces. But now we want to go ahead and go through the second part. My numerator is f of x plus h minus f of x. So I'm going to take this whole expression and I'm going to subtract the original function. So we get our first expression, f of x plus h, and we want to subtract our original function. So if you distribute that minus sign, we're going to see there's some cancellation. So the 3x cancels out. Then we also have -2x squared plus 2x squared. So those end up canceling out. And what's left over, everything has an h inside of it, which is good. I want to divide by h, so now I can go ahead and take that out. So we want to take this expression we just got and divide it by h. But since every single one of these has an h involved, we can factor that out. And now because it's factored out, we can cancel those two pieces and we get 3 minus 4x minus 2h with that particular stipulation that h is not going to equal 0. So kind of a key in each of these is the h in the bottom should always end up disappearing. If you're asked to simplify it, the h in the bottom better cancel. It might be as simple as you can factor out an h, but in some instances, if you're dealing with a square root or something, you might have to multiply by a conjugate. So just get some practice with these because it is going to be a very important concept.